Hey everyone, Dr. Crayhay here. In this Chapter 8 video, I'll be discussing statistical validity. So we'll talk about effect size, we'll talk about statistical significance, outliers, the restriction of range problem, and curvilinear relationships. One of the first things to consider when you're interrogating statistical validity is the strength of the relationship. And so one way to tell that is through a scatter plot. So here we have two scatter plots on the left-hand side, the top one A, the bottom one being B there. And so here you can see two variables kind of plotted against each other. So on the x-axis, of course, it's called x here, and then on the y-axis it's called y, and we're just saying, okay, so someone that scores a 3 on the x-axis, so you go over 3, they scored a 40, maybe a 42 on the y, so you go over to 3 up to 42 and you put a little point there, so each little point represents that person's scores on both x and y. So looking at this data as a whole gives you a sense of the strength of the relationship. So the clearer pattern that you see, the more clustered these are in a specific way, the stronger relationship you'll have. So both of these, both A and B, seem to have a relationship between x and y. They're both positive relationships, so that you can see as x increases, y also increases in both, but one of these relationships is stronger than the other. And so if you look at A, they're a little bit more dispersed. There's a little bit more variability there, so it's not as strong a relationship. When you look at B, on the other hand, they're much tighter, much closer together. If you needed to draw a line to represent all of these points, you could do that better than you could with that A scatter plot. So there would be more distance between your line and the points in A than there would be in B. So how strong is the relationship? If it's not a very strong relationship, you don't want to make a big deal out of it in research. Typically, stronger relationships or a stronger correlation will indicate a stronger effect size. So effect size tells you exactly what it sounds like. How large is the effect? How large is the relationship? How large is the difference, depending on your hypothesis. So here we're just looking at a relationship, and so A has a small relationship, a small effect size. B is probably a moderate effect size. So you want to pay attention to that. You can look at it visually, or you can tell by the size of the correlation. So of course, correlations closer to 1 will be stronger. They'll have stronger effect sizes. Correlations closer to 0 would indicate no relationship. So these are a couple of things to consider as far as the strength of the relationship. So this slide goes into a little bit more detail about what I was talking about in the last slide as far as strong correlations go, or the size of the effect. And so again, we have two scatter plots, A on top, B on bottom. And here it's showing you, so if we start with A on our x-axis, we have height at age 2, y-axis we have the height at age 15, and so you can see there's a positive relationship. So the taller you are at 2, the taller you'll be at age, I think that's actually age 18. Sorry, it looks a little bit small on my screen. And so again, if you have, so here they're talking about the participant Hugo, so you go over and when he was 2 years old, when Hugo was 2 years old, he was 83 centimeters, and so that's his X value. And then at age 18, he was 172 centimeters. So you go up, and then you plot his height right there. So he's that little blue dot. That's how you get all of these dots on here that give you a sense of the overall correlation. And so of course they do the same thing in B, except here they're looking at the mother's height and the son's adult height. Again, there's a positive correlation here, but based on what I told you in the last slide, you should be able to take a look at these really quickly and decide which one is the stronger relationship. So I'll pose that question right now. Which of these has the stronger correlation, the larger effect size? Is it graph A or graph B? Excellent. So you know that graph A is stronger because they're closer to that line of best fit, which is what this yellow line is that I keep referencing in these lectures. So you want to draw a line, and again this gets a little bit into statistics, but you draw a line that best represents every single point of data that you have. And so the lines here, those data points are more closely clustered together, so the line is a better fit. You have less error in A than you do with B, where you have more variability, they're more spread out, they're further from the line. And so stronger effect sizes really do give you better prediction because there's less variability, there's less error there. So stronger effect sizes lead to more accurate predictions, which is why we're concerned with this topic at all. So in this slide we start to consider statistical significance. And so statistical significance is a pretty confusing concept even for those of us with PhDs in this stuff. So basically, just to kind of boil it down to its simplest explanation, and it's not entirely, this won't give you the entire scope of what statistical significance is, but again, if you end up taking statistics, you'll learn much more, way more than you ever wanted to about statistical significance. So in this course, I'll just give you the overview. The general idea, and your textbook has a really excellent treatment of this, but statistical significance looks at the probability of obtaining this data that you have in front of you in a world where there is no effect or no relationship. And so you want that p-value to be very, very small. Just, I don't know, out of convention, someone a long time ago decided it needs to be, that p-value needs to be less than 0.05 to claim that there is an effect. Again, that's pretty much arbitrary, but it is the field's standard. It's less than 0.05 to have a relationship, to claim a relationship or difference. If it's greater than 0.05, you have to claim, no difference or no relationship, or you failed to find it in this case. So that's what this table is reporting. So if you see here, if you start in the rows, so we have an interaction variable alone, talking to others, we have small talk, so on and so forth, and then we can see intercoder reliability, the well-being index, correlation with well-being, satisfaction with life, correlation with well-being, so on and so forth. So you have a bunch of correlation values listed here, and then you have little asterisks telling you what those associated p-values are. So that here they have 2 asterisks means p was less than 0.01, 1 means that p is less than 0.05, so again it has to be less than 0.05 to claim that there is a relationship. That's really about all of the treatment that I want to give statistical significance in this course. Again, if you end up taking statistics, particularly with me, you will get more about this topic than you ever cared to. So just remember, statistical significance has to do with the probability of getting this result in a world where no result exists. So you want it to be very, very low. You want it to be less than 0.05. So if that statistical significance value, that p-value, is less than 0.05, you can claim that you have a relationship or you have a difference. If it's greater than 0.05, so 0.06, 0.07, 0.1, 0.5, it's greater than 0.05, you cannot claim a difference, you cannot claim a relationship. In this class in methods, I will ask you to use a p-value of 0.045. So think about that very carefully. Is 0.045 above 0.05 or is it below 0.045? That will affect how you interpret your results. So if you need to draw a number line, go ahead and draw a number line. That's perfectly fine to figure out if it's less than or greater than, because again, that will completely change your results section, and I do want you to make the correct decision with the information you're given. So less than 0.05, you can claim a relationship, you can claim a difference. Greater than 0.05, there's no relationship, there's no difference. Another thing to consider when you're looking at statistics in a study is the idea of outliers. So what is an outlier? That's anyone that doesn't score in a similar way as everyone else. And so there are different ways to define an outlier, and again, we'll get more in depth in statistics. But for now, you just know that they're different from the overall pattern of results. So here we have 4 different scatter plots, and you can see right away in those top 2 scatter plots, they're both A on the left-hand side and right-hand side, you have a cluster of people, and then you have one person that's kind of way out there. That person is the outlier. Same thing on the right there, so you have that little cluster of people, and then you have that person way out to the side. So oftentimes what you'll do is remove this person. There are different reasons for doing that. Sometimes you want to keep them in, and again, we'll get into all of that decision making if you take statistics. But for now, what you need to know is that outliers can greatly influence your correlation. They can greatly influence your overall results. Sometimes outliers will create a stronger correlation. Sometimes they will create a weaker correlation. It just depends on where they happen to fall in relation to that line of best fit. So on the left-hand side, on top, we see this data set with an outlier, and the correlation value is 0.37. Down on the bottom, we've removed this person from the data, and it actually decreased our correlation to 0.26. So that outlier was actually strengthening the relationship. And so of course the question then is, why did you remove this person if it harmed your correlation? Well, you want to best represent the people, you want to best represent the data. And so that person that scored way out there, they could be scoring like that because they misunderstood the instructions. Maybe they had some kind of learning disability that led them to take longer on your test. Whatever it is. So if there's something that makes them different than your sample, you definitely want to kick them out. And so that's what we've done here. We've kicked them out, and that way our correlation more accurately reflects our data and our sample, and then of course the population that we're trying to generalize to. On the right hand side, we're doing the same thing. Here we have a smaller sample, and so we have a bigger difference with and without the outlier. So here our correlation's 0.49 with the outlier. Same data set right below that in scatter plot B. It drops to 0.15 without that outlier. So outliers matter. They especially matter when you have small sample sizes. So in statistics, you'll talk about how to graph all of this stuff to look to see if there are any outliers. You might see some of this in some of your graphs that you're doing in this class. But just remember, outliers can affect your data. It's something you want to be considering. When you're reading published research, do they mention any screening for outliers, or did they just leave them in and push forward? Again, it could cause correlation, it could cause inflation, it could cause your correlation to go up, it could also harm your correlation. Outliers could cause your correlation to be lower than what you would actually have in your sample. So that's another thing to consider. We also have to consider restriction of range, and so here we have 2 scatter plots again, A and B, and we're looking at the relationship between SAT scores and college grades. So we know that SAT scores go from 1,000 to 2,400, and so we have that graphed here. Say that we have this data up top, data in scatter plot A. Our university only accepts SAT scores above 1,800. That's not true at IU East. I'm just saying in our example here, the university only accepts people with SAT scores above 1,800. Now, you can see the relationship between SAT score and college grades for all of those people at the university. The problem is you've cut off a big section of the population. So you don't know the relationship between college grades and SAT scores for anyone that scores between 1,000 and 1,800 because you don't have that data. And so it could cause your correlation to be lower than it actually would be in real life. And so here in scatterplot B down below, we have the full range of our data. So we have going from 1,000 to 2,400, the relationship between SAT scores and college grades. So you can see a much clearer pattern here. It would be much easier to fit a line here, so your correlation will probably be higher with all of this information. So when you restrict the range, you can artificially lower your correlation value. Also speaking in terms of generalizability, and I know that we'll get to this in a few more chapters, but generalizability is your ability to so you've taken a sample and you want to generalize to a greater population. So maybe you have a sample of college students and you want to see that their results are applicable to the United States as a whole, something like that. So when you restrict the range, so when you only look at SAT scores above 1,800, you're ignoring a whole part of your sample, which decreases your ability to generalize to college students in general. So that's another thing to keep in mind here. So you have an issue of artificially lowering your correlation value, and then this also impacts your ability to generalize your results. So when you're reading research studies, when you're writing up your papers, you want to consider, do you have the full range of data? So if scores from 0 to 100% are possible, do you have scores that range from about 0 to about 100? Or do you only have scores from 50 to 100? Because that would be a red flag for your restriction of range problem. So this scatter plot is showing a curvilinear relationship. So here you see, when you have age in years is 0, you have high use of the healthcare system. As you get older, 20s, 40s, it's a pretty low use. But then when you get up to, above 60, above 80, you start using the healthcare system quite a bit more again. And so this U-shaped curve indicates a curvilinear association. Correlations, any statistical test based on a correlation is going to be based on a linear relationship. So I keep talking about that line of best fit, that regression line that you probably talked about in intro algebra and maybe even in high school. It's just one line that fits all of the data. So if you tried to fit one straight line to this data in front of us, you would have a really hard time, and that correlation would be very close to 0, even though there is a clear relationship between age and use of the healthcare system. Just because of the way that correlation was designed, it's only looking for linear relationships. It's not looking for these curvilinear associations. So that's something that you have to be aware of. So you should always be graphing your data, be on the lookout for things like this in your scatter plot. If this happens, it's not the end of the world. It's just a signal that maybe correlation isn't the best statistical measure. And again, that starts to get into a little bit more complicated ideas than we want to talk about here in methods. But just know correlation is looking at linear relationships only. So if you have a curvilinear association like this one here, use of the healthcare system and age, correlation will not measure that appropriately, and you won't get an accurate representation of the relationship with a correlation.